Everybody, hope you're all doing well out there. Today we're going to be talking about the greenhouse effect. I know many people, yourself maybe included, would say the greenhouse effect is when the atmosphere traps heat. But in this presentation, we're going to get into the nitty gritty about what happens between photons of light and molecules that cause that quote unquote trapping of heat. I got a couple learning objectives for you. First of all, I want you to be able to describe what the greenhouse effect is, and then I want you to be able to model how light, particular visible and infrared light, behaves in the following situations. An atmosphere without greenhouse gases, we're going to start there as the simplest example. A glass greenhouse itself, and then finally an atmosphere with greenhouse gases. And then lastly, I want you to be able to evaluate how different substances alter the energy budget of an object and what that means for its temperature. All right, so a quick recap of electromagnetic radiation. We've studied this before, but electromagnetic radiation, or EMR, or light, is radiated energy moving as a wave or particle called a photon. We will be using that word a fair amount in this particular lesson, photon. There are 7 classes of electromagnetic radiation that fall in the electromagnetic spectrum, from low energy radio waves to high energy gamma rays. But when it comes to describing the greenhouse effect, 2 classes of light are important to us. We're going to be focusing on visible light, which is the class of EMR that our eyes can see, and infrared light, which is the class of EMR that is given off by all objects because of their temperature. The hotter the object, the more IR light given off. We cannot see IR light, but we can feel it as heat. So I'm giving off infrared radiation, so is my desk, so is my computer. I'm giving off more than my desk or my computer because I am warmer than those objects. And here we see the electromagnetic spectrum, just to refresh your memory on that. And again, we're focusing on visible light and infrared light right now. Kind of just disregard all the rest. Okay, and now I want to just go over a recap real quick of wave behaviors. There's only 4 wave behaviors we need to know to understand the greenhouse effect, and they are transmission, absorption, reflection, and emission. I'm not going to read this whole table. You could pause the screen if you want to check it out, but just so that we're aware, transmission is when light passes through a material unaffected. That's just passing through. Absorption is when light is captured by a material and converted into heat. That would be kind of like the death of a photon. Reflection is when light bounces off an object and is redirected backwards. So the energy stays as light, it's not converted to heat. And then emission is when new light is created by an object and radiated outward. So that'd be like the birth of a photon. And I give some examples as it applies to visible light and infrared light. Again, you could pause the screen and read those if you'd like. But here are just some simple models from a NASA website of these wave behaviors. And fortunately, we're actually taking out the most complicated wave behaviors. These are the 4 that we're focusing on. Emission is giving off, transmission is passing through, reflection is bouncing off, and absorption is capturing and converting to heat. All right, so one important piece when it comes to understanding the greenhouse effect is the idea that classes of light, like visible and infrared, can have different wave behaviors for the same object or material. So here we see the same image, one taken in the visible light spectrum with a regular camera, the other taken in the infrared spectrum with an infrared camera. And you can see here that in the visible spectrum, this plastic garbage bag that this man is holding is opaque. I can't see through it. And that means the light that is hitting it, the visible light that is hitting it, is either being absorbed or reflected. Because it's a black trash bag, I'd say more light is probably being absorbed, but there's still some light being reflected. You can kind of see that because it looks a little shiny. On the other hand, in the infrared spectrum, what I'm seeing is the man's hands very clearly through the bag, almost as if it were like clear plastic wrap in the visible light spectrum. So what this is telling me is that those infrared photons are actually being transmitted through the bag. The bag is transparent in the infrared spectrum. We're going to look at another example of this. Again, same idea. We've got visible light, regular photograph from a camera on the left. We've got an infrared image on the right. And here we're talking about glass, which is a very important object. We're going to talk about glass greenhouses. So glass is a great object to kind of get us to understanding greenhouse gases. And here you can see that this glass plate transmits visible light. I know that because I can see the man's hand behind the glass plate. But here in the infrared light is not being transmitted. I'm not seeing the man's hand behind the glass plate. And so that leads me to believe that that glass is absorbing and reflecting that infrared light. So again, classes of light can have different wave behaviors for the same object or material. I just want to make a quick note about objects and reflection versus absorption. If an object is transparent, it transmits visible light. That prefix trans is not by coincidence there, but not necessarily infrared light, as we saw just barely. If an object is opaque, which means it cannot be seen through, then it reflects and absorbs visible light, but again, not necessarily infrared. For an opaque object, it is not that the light only reflects or only absorbs. Both reflection and absorption occur in different amounts depending on the color and other characteristics. So don't think of it as one or the other, it's absorbing or it's reflecting. In actuality, black objects mostly absorb, white objects mostly reflect. And then a measure of an object's ability to reflect is called the object's albedo, which is the percentage of the light reflected. So just to look at this real quick, albedo equals the amount of light reflected divided by the total light coming in, and then turned into a percentage, and that light is reflected off. But there's still that other part of the 100%, the other slice of the pie that is being absorbed and converted into an increase in temperature. So just to give you a couple examples here, snow has an albedo of about 80%. That means 80% of the light's reflected, but there's still 20% absorbed. Water, on the other hand, has an albedo of about 10%. So only 10% of the light is reflected, leaving 90% to be absorbed. All right, so now we can jump into describing light behaviors in an atmosphere without greenhouse gases. This is the simplest model that we'll do and a good place to start. We're keeping in mind the two classes of electromagnetic radiation, visible and infrared, and we're keeping in mind those four wave behaviors: transmission, reflection, absorption, and emission. I actually even write the class of light in yellow if it's visible, red if it's infrared. I write the behavior in green and the object in blue. So the first thing that happens is visible light is emitted by the sun and transmitted through empty space, traveling towards Earth. Visible light is transmitted through the transparent atmosphere. Visible light is absorbed by the opaque surface of the Earth, and some is reflected, and that increases the temperature of the Earth. And then infrared light is emitted by the Earth, because anything that has a temperature is going to emit infrared light. And that infrared light is transmitted through the transparent atmosphere and eventually back into space. So that right there, what we just described, is called an energy budget. The sun's energy that is absorbed by Earth and the energy that the Earth radiates off back to space is called Earth's energy budget, and it regulates the temperature on Earth. It's basically the energy in and the energy out. I'm going to jump to a model real quick. It looks like this. It's a simulation, and bear with me while I get there. Here's the model, and what I want you to focus on real quick, I'm actually going to hide the cam, is note that there are two different types of photons here. Sunlight photons are yellow, and what they mean by that is they're talking about visible light photons, and infrared light photons are red. And what we want to do is we want to just look for those wave behaviors and those steps that we just described. So here we have a visible light photon transmitting. It hits the Earth and is absorbed. And then the Earth starts emitting infrared light photons, which travel back up towards space. They're transmitted through the atmosphere. And so we have energy coming in as visible light, and we have energy going out as infrared light. That is the simplest model of what we were just describing. And we have absorption happening at the surface of the Earth. All right, so at that, I'm going to jump back to the slideshow real quick. And we're back. So now what we want to jump into is, how does a greenhouse work? I'm not talking about greenhouse gases and the greenhouse effect. I'm talking about a greenhouse that you'd see on a farm. How does that work? We're going to be describing light behaviors in a glass greenhouse. So the first thing that happens is, just like before, visible light is transmitted through the transparent atmosphere, and we can see through glass, so we know that visible light is also transmitted through the glass of the greenhouse. The next thing that happens is that visible light is absorbed by the opaque plants and soil of the greenhouse, and it increases the temperature inside the greenhouse. And then infrared light is emitted by the plants and soil of the greenhouse because it has a temperature. But infrared light is transmitted through the transparent atmosphere, but is absorbed by the glass of the greenhouse. And that increases the temperature of the glass. Think back to that image of the glass plate with the person's hand behind it. We couldn't see their hand in infrared behind the glass plate because glass absorbs infrared light. So the glass starts to increase its temperature, and then the next thing that happens is infrared light is then re-emitted by the glass of the greenhouse in all directions. And I want to emphasize that. That's an important piece. It's in all directions. So some of that infrared light is emitted on the outside and does still head back towards space, but some of it is also emitted on the inside back down towards the floor of the greenhouse. And this means that about half of the energy is radiated back towards the greenhouse. The characteristics of glass allow all of the visible light energy to enter, but only about half of the infrared light energy to exit the greenhouse. This alters the energy budget and ultimately increases the temperature of the greenhouse by trapping in half of that incoming energy. Think of it this way, it's kind of like if you had the same amount of money going into your bank account, but only half as much leaving, your bank account would be bigger. In that case, your bank account is like the temperature. We see this not just in greenhouses, but also in cars. If you get in a car on a sunny day, chances are it's much warmer than the surrounding temperature outside, and that's because of the properties of glass. Transmitting visible light, but absorbing, heating up, and then re-emitting infrared light in all directions. So let's look at this model one more time. So I go back, what I'm going to do here is I'm going to reset and turn my screen off, and then I'm going to add a glass pane. We see that right there, that's a piece of glass. And we're going to look for those wave behaviors again. I'm going to slow it down and really just try to track a photon or two. So we've got a visible light photon coming in, transmitted through the atmosphere, transmitted through the glass, and then absorbed by the surface. I'm going to pause there. Then we see that the infrared photons are being emitted by the surface, and let's watch what they do when they hit the glass. They are absorbed by the glass. And now notice what the glass starts doing. It starts emitting new infrared photons. And sure, some of those are on the outside and are heading back towards space, but notice how others are on the inside and heading back down towards the surface of the greenhouse. This ultimately kind of pinballs the energy to be more concentrated in the greenhouse than outside of it. And we can see that is causing an increase in the temperature. If I were to speed this up, no longer just looking at one photon, I'm going to throw on some more photons. What we're looking for here is just a general kind of energy density. We can see that the greenhouse effect with the glass is causing the density in the greenhouse of energy to be greater than the density of energy outside the greenhouse. All right, back to the presentation. So that brings us to what is a greenhouse gas. And a greenhouse gas, sometimes abbreviated GHG, is an atmospheric gas, it's in the atmosphere, that acts very similar to greenhouse glass. So a greenhouse gas is just like a greenhouse glass. Visible light is transmitted through transparent greenhouse gas molecules. By definition, I can't see a greenhouse gas molecule. They're transparent. But infrared light is absorbed by the greenhouse gas molecules, which increases the temperature of those greenhouse gas molecules. And then that infrared light is re-emitted by the greenhouse gas molecules in all directions. So again, some would be re-emitted back towards space, but others would be re-emitted down back towards the surface of the Earth. Despite our inability to see and feel them, like we can the glass of a greenhouse, greenhouse gases trap energy in the atmosphere of Earth, much like the glass of a greenhouse traps energy. In small amounts, this is good. Without some GHGs, Earth would be too cold to support life. So we do need a little bit of a blanket from those greenhouse gas molecules, adding some energy to the atmosphere to keep the general temperature of Earth above the freezing point of water. But do know that the amount of greenhouse gases is very small relative to the rest of the atmosphere. Nitrogen gas, N2, and oxygen gas, O2, together make up 99% of our atmosphere and are not greenhouse gases. Carbon dioxide, CO2, and other gases are greenhouse gases. So we're going to just pop up to that simulation again. And here we're going to look for what we just described. Here's a nitrogen molecule, N2. And I'm going to start shooting visible light photons at it, and we can see that they're transmitted. They pass right through. I'm going to also shoot infrared light photons at it. We can see that they're transmitted. They pass right through. The same is true for oxygen. It transmits both visible and infrared light. So those are not greenhouse gases because they are transmitting visible and infrared light. Those are non-greenhouse atmospheric gases. And again, those two are 99% of our atmosphere. But if we were to, I wanted to select carbon dioxide, but my screen, my webcam's in the way. So I'm going to show you a different greenhouse gas, water. And what I want you to look for here is this greenhouse gas, in this case water, but also carbon dioxide, is transmitting visible light. But watch what it does to infrared light. It captures it, it wiggles, and then it shoots it off in a random direction. The capture is absorption. The wiggle is the increase in temperature. And then the shooting it off in a random direction is that re-emission in any direction. Any direction means some of it's back towards Earth. All right, and at that, we're going to pop back to the presentation. Almost there. So here's a quick summary of visible and IR wave behaviors for different materials. A non-greenhouse gas, like nitrogen and oxygen, 99% of our atmosphere, will transmit both visible light and infrared light. Glass and greenhouse gases are identical in this particular table. Glass and greenhouse gases like carbon dioxide transmit visible light. I can see through them, but they absorb, increase their temperature, and then re-emit infrared light in all directions. And then the surface of Earth, which is opaque, is going to either reflect back visible light or it's going to absorb and increase its temperature for visible light. And then the same is true for infrared light. The surface of the Earth will absorb infrared light, its temperature will increase more, and it will re-emit that infrared light back up into the atmosphere. So hopefully that table is helpful to kind of put this all together. And this brings us to our last piece that I would want you to be able to model, which is what is the greenhouse effect? Describing light in an atmosphere with greenhouse gases. So visible light is transmitted through the transparent atmosphere, because whether it's a greenhouse gas or a non-greenhouse gas, it's transparent to visible light, and absorbed by the opaque surface of Earth and that increases the temperature of Earth. So we get energy from the sun. Infrared light is then emitted by the surface of the Earth. And then here's where it's different from the atmosphere without greenhouse gases. Infrared light is transmitted through the transparent nitrogen and oxygen in the atmosphere, but absorbed by the greenhouse gas molecules like carbon dioxide, increasing the temperature of the greenhouse gas molecules. They wiggle, and then that infrared light is re-emitted by greenhouse gas molecules in all directions. Again, that's an important piece, in all directions, meaning about half of the energy is radiated back down towards Earth. So what does this mean? Adding more greenhouse gases to the atmosphere, or adding more layers of glass to your greenhouse, is the equivalent of adding more blankets when you sleep at night. It changes the energy budget, the amount of energy in versus the amount of energy out, and it increases the temperature and is called ultimately the greenhouse effect. So we're going to pop back to that simulation one more time to see the greenhouse effect in action and what it means for these photons. So here I've got the greenhouse gas concentration. It's set down to none. And you can see again, yellow is visible light, red is infrared light. When we run this simulation with none greenhouse gases, no greenhouse gases, we get transmission of visible light, absorption by the surface of the Earth, and then that infrared light can stream basically unrestricted back towards space. So energy coming in as visible, energy exiting as infrared. The net result of that is a very cool planet. Let's slow this down. Transmission of visible light, absorption, emission of infrared light, and then transmission back towards space. Hopefully you're seeing those wave behaviors in the simulation. Let's now reset this. And what I want to do here is I'm going to just play with the extremes. I'm going to max out the greenhouse gas concentrations. I'm going to slow it down, and we're going to see what we can see here. All right, we've got transmission of visible light. That visible light is absorbed by the surface of the Earth. And now let's look at some of these infrared light photons. They're pinballing around in the atmosphere. And with each of those changes of direction, what happens is a greenhouse gas molecule absorbs the infrared photon, it heats up, it wiggles, and then it re-emits it in any direction. And that's what causes these greenhouse gas photons, or these infrared photons, to be changing their direction constantly. By changing their direction constantly, it means it's much harder for them to exit out into space. That energy is much harder to be gotten rid of. And the net result here is we're starting to see a higher energy density of infrared photons as they pinball around near the surface of the Earth. If I were to, say, view all photons, we can see here that the energy density towards the surface of the Earth is greater than the energy density up here towards the top, because those greenhouse gases are acting like a blanket that is throughout the atmosphere. And I'll just speed it up to show you lots more photons than if we, again, were to knock this greenhouse gas concentration down to nothing. Now all of those photons go up towards space, unrestricted, because there is nothing to absorb, heat up, and re-emit those photons in the atmosphere. I hope that was a helpful, not too complex way of understanding the greenhouse effect through absorption, emission, transmission, reflection, and what it means for the planet and its overall temperature. You've got some associated questions in your assignment, and feel free to let me know if you have any questions about anything I've said here. And I can paste a link to this particular simulation in the assignment if you want to check it out. But just a quick disclaimer about that. This needs Java to run, which your Chromebooks don't have, unfortunately. If you go on a Windows PC, you'll be able to run this by searching PhET. That's PhET with a PH, like you see right here. and the greenhouse effect. So Google PhET with a PH and the greenhouse effect. Other than that, be well, guys, and I'll see you when I see you. Bye.